Section 2.3 is about evaluating limits analytically. So last time we were able to do it graphically and we were able to do charts, and what we realized when evaluating limits was there were some times where there was nice functions where we could just plug in the number, and then there was other times when they weren't nice, where it was undefined at that point, or maybe it was defined at that point but it wasn't the same as the limit, etc., etc. So the question then becomes, how do we do it if we don't want to use a graph, if we don't want to use a table? Are there other ways we can do it? Essentially, when can we just plug that limit in, and are there different techniques that we could do algebraically where we don't have to do those tables and graphs? And the answer is yes, and that's what this section is about, and they call it solving them analytically. So it says in section 2.2, you learn that the limit of f of x as x approaches c does not depend on f at x equals c. In other words, what I used to say was it doesn't matter what happens at that point, it only matters happens near that point. It says it may happen, however, that the limit is precisely f of c. In other words, where it's saying it may actually occur where you can actually plug in that x value and it is the limit. It says in such cases you can evaluate the limit by direct substitution. That is, the limit as x approaches c of f of x. In other words, if you want to find the limit for a given x value, just plug that x value into the function. It says such well-defined or well-behaved functions, those are what I call nice functions, are called continuous at c. You will examine this concept more closely in the next section, 2.4. But here are some basic limit properties. It says, let b and c be real numbers and let n be a positive integer. Then it says, let x approach, or the limit as x approaches c of b equals b. So again, remember that this inside function right here, this b right here, that's your y value. That's your function. That's your f of x, right? So let's think about why this must be true. Consider a function, I don't know, let's do an example. How about y equals 3? Let's consider y equals 3. So what if we wanted to find the limit as x approaches 5 of y equals 3? What would that equal to? Okay. Well, let's consider that function. What does y equals 3 look like? Well, every single point, your y value must be 3. And if the y value stays the same, think about what that would look like visually. That would be a horizontal line. That's y equals 3. No matter what point you choose, your y value is 3. Okay? So now let's consider when x equals 5, right? The question is, what happens as we come from the left and what happens as we come from the right? Well, notice your y value every single time is 3. And a limit is asking, what's your y value approaching? Well, the y value is approaching 3. It's a horizontal line. The y value is always 3, so it always approaches 3. Notice that the x value here, we said x equals 5, that absolutely doesn't matter. If we went to any value, what if we considered the limit as x approaches negative 2? So if we change that to negative 2, that doesn't change the y value at all. The y value is still 3. So it doesn't matter what value we're approaching for x, we're always approaching the y value of 3. So that was y equals 3. What if we did y equals 5 or y equals 10 or y equals negative 20? Would that change? Well, no, because it's always a horizontal line. So it doesn't matter what x value we choose. If you give me the y value, the answer is always going to be that y value. So that's what the first one is there. The way that I would say this is the limit of a constant is the constant. So let me write that out for you. The limit of a constant, like y equals 3, is the constant. Okay. Let's look at the second one, see if we can make any sense of this. It says the limit as x approaches c of x is c. So let's think about the graph here. We're looking at, remember, this is always our function. That inside one's always our function. So we're looking at y equals x. Well, do you know what the graph of y equals x looks like? I'll come over here to the right and I'll do it. Here's the graph of y equals x. It's the diagonal line. Notice your y value is always your x value. So think about what happens when x equals 2. What would my y value approach? It would be 2. Think about if it were an x value of negative 3. What would my y value approach? It would be negative 3. So no matter what your x value is, or whatever your x value is, that's what your answer is. And so if you look over here and you notice in the rule, you give me the x value, that x value is the answer. So the limit of x is that x value. The limit as x approaches c is c. The limit as x approaches c is of x is c. Okay? Likewise, the next one works. The limit as x approaches c of x to the n. All that's saying is we can raise it to a power. As long as it's a positive integer, we can raise it to that power. It doesn't always work for every number, but it does work when your power is a positive integer. What are they talking about here? They're just talking about something like x squared, x cubed, x to the fourth. I mean, pretend if you not pretend, visualize something like, I don't know, here's x cubed, right? And if you're thinking about x equals 1, well, the y value is 1 cubed, which is just 1. And if you go to 2, the value would be 2 cubed, which would be all the way up to 8, right? Okay, so all it's saying is you can just plug in the number. That's the nice part there, is you can just plug in the number. So that's what the next one says. That's what the limit as x approaches c of x to the n equals c to the n. Essentially, it says if your function's just x, plug in the number. If your function's x to the n, plug in the number. Okay? So let's see these in action. Let's look at example 1 here. Example 1a says, what's the limit as x approaches 2 of 3? Well, this is a constant, and we know the limit of a constant is the constant. So the answer is 3. I got to show some type of work here, so I'm just going to say constant, and that's what it is. Because it's a constant, the limit of a constant is the constant. Notice the x value here did not matter, because no matter what your x value is, you're dealing with a horizontal line at y equals 3. Let's look at the next one. It says the limit as x approaches negative 4 of x. Well, this is simply x, and the beautiful thing about x is we know we can just plug in the value. So the answer would be negative 4. Showing work for this problem, not too easy. You could just say it's x, or you could just circle the x, or you could just circle the x value. I just wrote here negative 4. That's perfectly fine. C is the limit as x approaches 2 of x squared. What do you do for the limit as x approaches 2 of x squared? Well, again, that's x to a positive integer. It's a nice value here, so all we have to do is plug in the x value. 2 squared is 4. We've shown work on the problem. There's our final answer. So that's the basic rules. Theorem 2.1 gives us some of the basic limits. The limit of a constant is a constant. If it's x or x to the n, just plug in the x value. But we can extend it to more rules. All of these can be proven and are proven in the auxiliary section. They might even be proven in the textbook in the normal pages. But you can see proofs of these in the appendix. No need to know the proofs of them. I'm not going to test you on the proofs of them. I do need you to know the rules, though. So what's the first rule? The first rule says, look, we know for the limit of x, you just plug in that value. Or the limit of x squared, you just plug in that value. But what if I had the limit as x approaches, I don't care, c, of 5x squared? Or 3x? What do you do when you have that coefficient out in front? That coefficient is called a scalar multiple. So what do you do with that coefficient? So if I found the limit of 3x squared, all I would do is plug in the number into x squared and then multiply it by 3. So all that's saying to do is keep the coefficient out in front. Keep the coefficient. You can pull the coefficient out in front. What's number 2 saying? Number 2 saying? It actually says two things. It says the limit as x approaches c of f of x plus g of x equals L plus k. And it says the limit as f of x minus g of x equals L minus k. So what if I had x squared plus 3x plus 5? Well, I could find the limit of x squared, I could find the limit of 3x, and I could find the limit of 5. And then I could just add each one of those answers together. So what this rule does, and it's an extremely important rule, is lets us find the limit of each individual term, each piece, and then put them all together by adding or subtracting them together. So we can separate polynomials now and find the limit of each piece individually. Number 3 is the product rule. It says the limit as x approaches c of f of x times g of x equals L times k. What that's saying is find the limit of f of x, find the limit of g of x, and then just multiply them together. So find the limit of the first one, find the limit of the second one, then multiply them together. So what this is formally saying is the limit of the product is the product of the limits. Let me say that again. The limit of the product is the product of the limits. Likewise, number 4 is quotient. Remember, quotient means division. So what if we had the limit as x approaches c of f of x over g of x? Well, what this rule is saying we could do is we could find the limit of the top and the limit of the bottom and then just divide them. We got to be careful here though. Remember, with any fraction you can never divide by 0. So all that's saying that k not equal to 0 is just saying, look, you can't divide by 0, so it's not true when the denominator is 0. But the formal rule says the limit of the quotient is the quotient of the limits. The limit of the quotient is the quotient of the limits. Number 5 would be the power rule. Power rule is the limit as x approaches c of f of x to the n. So instead of just doing x cubed, what if we had 2x plus 3 quantity cubed? What could we do? And what number 5 says is find the limit of the inside and then raise it to the power. So you would find the limit of 2x plus 3, and then you would raise it to whatever power it is. Okay? So you can bring the limit inside powers. So let me write down and summarize kind of what we just said. The first one says pull coefficients out in front. Coefficients are scalar multiples. The second one says separate addition and subtraction. Do each part individually. The third one says separate multiplication. Just do each part individually. The fourth one says separate division. The fifth one, a little more complicated, says evaluate the limit of the inside first. Okay, so all these rules, different rules, are going to be used multiple times. And I can't express to you the importance of this. In calculus, we're going to learn, Calc 1 anyways, we're going to learn 3 primary things: limits, derivatives, and antiderivatives or integrals. Well, all derivatives are limits, and all antiderivatives are derivatives backwards, which are limits. Okay, so everything builds on this foundation of these rules right here. Virtually every rule that we learn comes from the foundation in this theorem right here for all of calculus. So extremely, extremely important that you know. With coefficients, you pull them out in front. With addition and subtraction, you can separate them. Multiplication, just do each part individually. Division, just do each part individually. And then you can evaluate the limit of the inside first and then raise it to the power. We'll see all of these in actions in the next pages.